A photodiode is a kind of photodetector. These optoelectric devices have the ability to convert optical signal into electron-hole pairs, converting light into a voltage into a current, depending on the bias and external circuitry. This class was divided into halves. On the first half, we analyzed the effects of adding a series load resistance and parallel capacitance. On the second half, we analyzed the photodiode responsivity to different wavelengths and understood how different materials would behave.
In this video, we will explain a simple methodology to observe the response times of a photodiode and how it is affected by internal resistance and junction or parasitic capacitances. In this case, we use the PIN silicon photodiode. To determine which is the positive terminal, P side, there is a little dent, and when comparing it with the datasheet, we can see that the terminal with this dent corresponds to the positive or P side. A light source is also needed. In this case, we use the green laser. To control the frequency of the light, that is, to modulate it, we use the chopper. This chopper is connected to an oscilloscope, so we can observe the reference signal that is delivered to the photodiode, which was assembled in a proper support. In order to observe the effects of the internal resistance of the photodiode in its response profile, we use a resistor box which allows for varying resistance values. Similarly, a capacitance box is also necessary to simulate the effects of parasitic capacitances and/or to observe the effect of the junction capacitance. The resistance should be added in series and the capacitances in parallel. This way, we should also be able to observe, in a practical perspective, the effect that both of these components have in the photodiode's response time. This response was observed using an oscilloscope, hence the terminals of the system photodiode plus resistance should also be connected to it. Note that, since a photodiode is a device which generates electrical current when light stimulated, it would be of good practice to measure its output current, but since an oscilloscope does not measure current, we observe the device's response in terms of the voltage across the system photodiode resistance. This way, the resistor acts as the photodiode's internal resistance, and it is possible to affect its implications. Here, we present a schematic of this assembly. A voltage source is also necessary to reverse bias the photodiode. This type of device should always be reverse biased to enhance the already present junction-driven electric field. A stronger electric field will properly separate the electron-hole pairs created by the incident photons and accelerate those free carriers, guiding them to the device's terminals. Next, a starting value of 300 ohms was set on the resistance box. Observing the response of the photodiode in the oscilloscope, we can see that it is pretty much in conformity to what would be ideally expected. As we increase the resistance value, we notice an elongation in the fall part of the curve, that is, the fall time increases while the rise time stays unchanged. This means that the photodiode continues to output current a bit after the light stimulus is removed. So, why does this happen? When increasing the resistance, we are basically making it harder for the free carriers to travel across the device and reach its terminals. This mostly affects the slow carriers, which are responsible for the fall time increase. This effect is very critical because at high frequencies, the photodetector is not able to fully discharge, cutting significantly the current output. When the amplitude of the photodiode's response is cut by half of its maximum, we say that the device is cut off. And how do we fix this? Imagine you had a photodiode that had this response profile due to high internal resistance, or with a very extensive intrinsic region. It is possible to attenuate the effect of the slow carrier's response by increasing the reverse bias modulus, which means increasing the electric field intensity. This should be enough to provide the slow carriers with enough acceleration to improve the fall time of the device, meaning that the current output won't be carried out for so long after the light stimulus is removed. Next, we aim to observe the effects of parasitic or junction capacitance. For this, we set the resistance value to about 200 ohms. To understand what we are about to simulate, let's take a look inside the photodiode. The outer layers are both doped semiconductors, and the middle layer is an intrinsic one. A not-so-conductive layer between two reasonably conductive layers acts as a capacitor. As we know, the capacitance of a capacitor is given by this expression. If we change the intrinsic region's thickness or area, the photodiode's junction capacitance will be altered. Accordingly, we raise the capacitance value with a capacitance box. Since the area is not possible to change, a raise in capacitance will simulate a thinner intrinsic region. We observe that both rise and fall parts of the response profile both curve, getting to a sawtooth type shape. This creates the same problem as increasing the internal resistance of the photo device, meaning that if we increase the light frequency, the photodiode will be unable to fully discharge and its response will be cut off. Contrarily to what we've seen before, increasing the reverse bias modulus won't solve this issue, since we're just simulating the intrinsic area getting thinner. The responsivity of a photodetector relates the response of the device in function of the stimuli it receives. It is given in amperes over watts for a range of wavelengths. In the datasheet, it is possible to see what is expected from the measurement. Observing the expected response, it is possible to see that the response time of a photodetector has an associated cut wavelength, corresponding to the energy below or the wavelength above the energy gap of the material. The device starts to respond at wavelengths lower than 1100 nanometers, since it's where the energy of the incident radiation starts to match the energy gap of the material, and so it starts absorbing energy. The value of the absorption coefficient increases for larger values of energy, but the photodetector response decreases. That can be explained in the following way. When light hits a material, 86% of it is absorbed at a thickness equivalent to 2 over alpha. So, if the absorption coefficient enlarges for smaller wavelengths, the thickness of material necessary to absorb the light will also decrease, and, this way, the light is absorbed more and more at the surface. With this, the radiation might be absorbed in the doped part of the surface of the device. Generating electron-hole pairs in the doped area leads to an instant recombination of the minority carriers, decreasing the response of the photodetector. So, the material is actually very absorbent in these wavelengths, but it happens very close to the surface in doped areas, reducing the response of the photodetector. The type of photodetector has an influence on the responsivity measured. In the example studied in this video, a homojunction photodetector, both the N and P sides are made of the same material, silicon, that present similar energy gaps. Doping in silicon has almost no effect on the energy gap. This provides a responsivity graph like the one seen on the datasheet. In a heterojunction photodetector, the N and P sides are composed of a material with an elevated energy gap value and separated by an intrinsic layer. This generates a trapezial-shaped response, since the radiation starts to be absorbed in the intrinsic layer with the smallest energy gap and maintains a relatively constant absorption. With the increasing energy, the absorption happens each time closer to the interface of the intrinsic layer, until the responsivity decreases abruptly, because we get to an energy value corresponding to the gap of the doped area, so the absorption happens there and is diminished for the aforementioned reasons. What is necessary to determine the responsivity of a photodetector? A current meter, a light source, white light so that a variety of wavelengths can be analyzed, a monochromator in order to select the wavelength that hits the sample, a chopper that allows to obtain the response of the photodetector only with the ambient light and with the incident plus ambient light. This way it is possible to do a baseline and remove the background noise. The chopper could be dismissed in a dark environment. A bandpass filter to cut off the harmonics of the wavelengths that, despite having a low intensity, can interfere with the readings. A beam splitter that divides the incident radiation in two, and each bundle of light goes to a different site, either the sample or reference detector. The latter has a known responsivity, so it is possible to determine the optical power incident on the reference detector and on the photodetector sample. The beam splitter can divide the radiation in different fractions, and it is suitable for this type of systems as long as we know how it divides the proportions of light, allowing us to determine the relation between the optical power that arrives in the reference and sample photodetector. A reflection meter to monitor the amount of light that is lost by reflection, either on the encapsulation or on the photodetector itself. As expected from the datasheet, the responsivity is in the 400 to 1100 nanometer range, with a maximum value of 0.6. When evaluating the response of the reference detector, we have a few disparities when compared to our silicon homojunction photodetector. First of all, the peak corresponding to the maximum value happens for larger wavelengths, meaning that this material has a smaller energy gap. The maximum value in this detector also shows a maximum responsivity very high, around 0.9, which is not typical for silicon. We can conclude that the reference detector is, most likely, a mixed detector, combining different types of materials with different responses, so that there is a sum in the responsivity when the response of the materials overlap.
With this, we conclude our brief analysis on photodiodes. Stay tuned for LEDs class next week.